from Romania, and I am managing now a company, Plasmaterm, which is dealing with investment casting and surface engineering, two different departments. In surface engineering, we are mostly qualified for plasma processes, and we run plasma processing equipment practically around the clock. Well, my background is a mechanical engineer, so I am not coming from the metallurgical side of surface engineers, but from a mechanical side. And I was heading for a very long time a research institute studying wear phenomena, fatigue phenomena, and the effect of surface engineering on these phenomena. Then in the last 10 years, as I said, I am managing this private company, and I am also associated professor teaching material science and surface engineering. And really, I consider this is an outstanding, beautiful subject. It's an interdisciplinary area where you can play as much as you wish with the properties of materials and the processes which may influence the properties of materials. That's why it's so attractive for me. Well, what I will try to present you today is a kind of an integrated case study. And I should like to explain why did I choose to present an integrated case study instead of a lecture. It's not just because in the Innovate we have a task to put on the platform such case studies, but also it's something more. Well, I try to connect the scientific side with the practical side, because I always consider it's much more attractive to have both science and practice at hand, and an integrated case study, it seems to me, is the best to show both the theoretical and the practical side of the problems. Such a case study gives us always an idea about a problem to be solved and about the methods how do we can solve these problems. Well, I must tell you, do not consider that everything which is given in the case study is 100%, let's say, as it is in the industrial application. It's a little bit distilled. It's distilled for a presentation. And another thing, that this presentation is definitely not an e-learning presentation. You will find an e-learning presentation on internet, on our Innovate program. This is a shortened version which was prepared to try to give you an idea on the philosophy of this case study, and certainly to allow me to present in this way some of the ideas connected to the case study. Well, what was the starting point? That all the engineering components may be manufactured using different materials and different processes. Definitely, you cannot say there is the best process and the best method. No, we have just optimum or optimized processes for a given purpose, which will consider always the technical side and the economical side. Because in industry, you know very well, most of you are from industry, you know very well, we cannot just neglect the cost side. Everything costs money. And in any company, the economical control is very strong. So when we want to do something, we want to solve something, certainly we always have to consider, first of all, the technical task, but we have to consider also the economical side of the problem, because otherwise we definitely will fail. Either our boss won't accept the method, or the acceptance, a larger acceptance, will be denied. Well, so I just was choosing a main shaft for the industrial high-speed sewing machines because it's fascinating. I will show at the end of the presentation a short animation just to have an idea what that means, which is the component. But accept it is a small component, is like that. Well, it's a small component of the overlock sewing machines, which is still extremely interesting because we all think, well, what the hell is a sewing machine? It's just a shaft is turning, a needle is moving up and down, and then it's practically is a very low solicitation. So no, that's not true. An overlock sewing machine, which has such a camshaft, the main shaft, with the typical dimensions given here, is running at a speed between 10,000 to 15,000 per minute, and it's starting and stopping about 20 times a minute. You can imagine what that means. A start time or a run-up time is about 100 to 140 milliseconds, and the stop time, when a stop motion unit is coming into picture, is about 70 microseconds. So it's fantastic indeed. When you consider what a solicitation such a part has, then you can understand why did I choose such a part for a case study, because indeed from all the points it's a very interesting one. High accuracy is needed, narrow tolerance field, you see I gave some of the data here. And it's typical because without changing the material, you see, is the standard material which is used is, according to the German norm, a low alloyed chromium manganese steel, which is very widely used. On my view, is a very good steel because it responds very well to any kind of treatment and not expensive, which is also not to be neglected. And without changing the material, we can obtain real benefits, changing just the technology and the surface engineering. In this integrated case study, I consider certain the case presentation I just shortly made. The expected properties, we come back to the expected properties, the theoretical background, experimental technology, productive evaluation results, economical considerations, and certain conclusions. This is which I considered as a typical structure of such a case study, trying to answer most of the questions concerning the technical side of the problem, but also the economical side of the problem. So, today, most of the companies are manufacturing such kind of shafts from the steel I just have shown you. It's 16 chromium manganese 5, which is a very common steel. And they use carburizing as surface engineering process. What's the problem? Certainly is a good one, but if you consider that such an industrial overlock sewing machine starts and stops so many times, just as I said, it's very clear for everybody that no hydrodynamic lubrication is possible. It's practical what we have is a kind of a boundary lubrication, but we have always to consider some dry spells as well, because you cannot lubricate the parts abundantly, it's clear, because otherwise you will have stains on the textile. The thread will be stained, so it's impossible to use a huge amount of oil. So you have to use just a drop of oil, which will cover the needs for lubrication. So this is one of the problems. But there is another problem as well. Due to the very narrow tolerance field, which I just have shown is within a range of about 5 microns, when you treat such a part by carburizing, that means you will have to go through a long process chain, manufacturing, machining and heat treating, stress relieving, and so on, because the part, as you have seen, is very sophisticated, and you always cut the structural lines, which will introduce a lot of deformations. Certainly, when we treat the part at high temperature, which is around 900 or 870 degrees centigrade, and we quench, the deformation cannot be avoided. And after deformation, straightening is very difficult for this high precision, and you definitely will have to apply after machining, post-machining, you have to apply a grinding and finishing, which is a very costly process. I was given a task years ago to try to find a better solution, and then we tried to change this. It's just illustrating a scanning electron microscope picture of the worn surfaces. This is a very bad one. So when it's an advanced damage may be observed, this is not only due to the adhesive type wear, but also because of the presence or high presence of some abrasive particles, because the polyacrylnitrile thread is something awful. During operation, very fine debris of this fiber are entering into the structure of the machine, and they have a very, very strong abrasive effect. It's one of the biggest problems with most of the textile machines. Well, just in a parenthesis, I find textile machines very fascinating because they are so complex and they give such a lot of problems that you have always headache. How can you solve? Because you solve one problem and two others will appear immediately. The carburizing does not respond to all the requirements for such a production. So then we choose to replace carburizing by plasma nitriding nitrocarburizing. You will see there's a little bit of incoherence in the terminology what I used, because we applied both of these technologies. We applied plasma nitriding and we applied plasma nitrocarburizing. At the beginning, we performed plasma nitriding. That later on, we shift to plasma nitrocarburizing because of some reasons which I will tell you. So that's why you will find both of them. Well, carburizing does not change the character of the material. We just introduce carbon in the surface, which will give a higher carbon martensite in the surface, and certainly this will lead to a typical carbon gradient in the surface, and certainly this typical carbon gradient will be reflected also in the hardness plot, hardness against the depth. It's well known for you, for all of us. So that's typical for carburizing. The problem is, just as I said, is the distortion, quenching, the dimensional changes, which make then you need strengthening and you need post-machining. And you have seen the typical damage of the surface in process. Well, when we shift to nitriding or nitrocarburizing, because in this respect there are not two big differences between the two, you will have a compound layer on the surface which is consisting of nitrides or nitrocarbides. Then you will have a diffusion layer which is containing nitrides of the alloying elements, and it gives a support. This is a support layer, and then the substrate. So this compound layer, the nitride compound layer, epsilon or gamma dash compound layer, has an excellent wear resistance, and the wear of such a layer is completely different from the wear surface we have seen. Well, you see, this is a worn surface after quite a long running time. I shouldn't say how long. Well, you do not see this typical damage which I have shown on the other side. And this is at higher magnification in some places. You see the traces, but no scuffing or seizure occur. First, we began to treat the parts not by plasma nitrocarburizing, but by gaseous nitrocarburizing, low temperature nitrocarburizing. Well, certainly then later we shifted to plasma, because plasma has a lot of advantages. First of all, a low energy consumption, shorter treating times, a very good reproducibility of the results, so less manufacturing reject and cost. Then practically no distortion appears due to the low treating temperature, and a very low active gas consumption. So the main disadvantages of this kind of DC plasma process is that the uncontrolled hollow cathode effect may produce local overheating, And we had this problem at the beginning with the shafts. Between the two surfaces, due to this effect, we had an overheating, and the results were not always uniform. Certainly, the uneven heating of different parts could appear when you try to put different parts in the same load in the furnace, which caused also problems. This probably will be solved by active screen treatment, which is a new procedure and probably heard about in the lecture of Professor Bell. Well, I just explain here briefly, and I do not want to enter here in details, because as you also heard in the lecture of Professor Bell, the plasma nitrizing is a low-pressure glow discharge process, and the nitrocarburizing is the same, but instead of a mixture of dissociated ammonia, so practically nitrogen and hydrogen, we add also a gas which will be able to deliver carbon, and this is in our case is methane, so we use methane for delivering carbon. This is a schematic representation of the DC plasma nitriding unit which we use. It's the vacuum chamber, so connected to a vacuum system and a pressure gauge. It has a specific gas supply, which is either from a mixture of nitrogen and ammonia from bottles, or in our case, we use dissociated ammonia, and we add methane for hydrocarbon, and certainly electric supply and control system. When we consider the technology, there are a couple, it's shortly illustrated, the whole technology is illustrated here. So first of all, we need a cleaning and degreasing, which is extremely important for nitriding or nitrocarburizing. It's much more important than for carburizing, because here the temperature being low, the surface activation is extremely important. And we were dealing for many years to study the influence of surface activation on nitriding, so what happens when some passivated layers appear, and passivation will not necessarily always disappear just due to the cathode sputtering. Then the loading, which has to follow a specific structure just to assemble the parts so that we can have a glow discharge as uniform as is possible. The next one, when we start the process, first, it will be a sputter cleaning of the parts, which will remove practically all the oxide traces and anything from the surface. And then certainly we come to the treatment, which is at temperature of 500, 510 degrees centigrade, at a pressure roughly 2 torrs, duration 5 hours for this pieces, cooling generally slow cooling under vacuum conditions. That's what we apply here. And certainly then the parts are removed, tested, and packed. Well, it's extremely important now, and it's something which I should like to emphasize inside the case study. This part of testing the results of the treatment. So we have 2 different systems for testing the results. One of the systems is concerning the product development phase, because certainly to test in the production all the parts according to a rather sophisticated system is almost impossible. That will cost much too much. So for the development processes, we will test not only product geometry, like dimensional accuracy, surface roughness, but surface properties like metallographical examination of the microstructure, microhardness in compound layer and the depth profile. And we also perform wear tests on without lubrication or with lubrication, boundary lubrication. We have quite a range of possibilities to test the wear properties of the surface using a kind of Phalanx machine, which we developed ourselves to match exactly our needs. And we are also able to measure rather accurately the coefficient of friction of the surfaces, which also gives a very important indication. But certainly, this is a rather complicated test system, which should cost a considerable amount of money. And that's for shop floor quality assessment. We certainly will control the product geometry and the surface properties like visual examination, cross-layer hardness test, and metallographic examination when that's requested on some samples. Typically, the product geometry considers dimensional changes up to maximum 4 microns in diameter. And this is a rather good value. The deformations inside of this tolerance field were about 2 microns, so a really very, very good result. And the surface roughness around 0.8 microns RA. Well, this is a typical structure of the layer where you have a compound layer of 10 to 20, but normally around 15 microns, and mostly this compound layer is an epsilon type layer, so not pure epsilon, it has gamma dash as well, but basically epsilon, because according to our experience, the best results in sliding friction we can get from epsilon type layers. Then we have a diffusion layer which is roughly between 0 to 0.3 millimeters, and we have no discontinuity of porosity in the compound layer. It's clear, you can see it clearly. And the cross-layer hardness of about 600 Vickers, and the compound layer has roughly a hardness of over 750 to 800 Vickers. And we give here a typical micro hardness plot and 3 different positions of the shaft. So that means that we achieve very well the technical goals with this new technology. And the steadiness of the results, the reliability was excellent, was better than in case of carburizing. And there is an important aspect to emphasize here, a real practical one. You know that different lots of steel from the steel mill will come with slightly different properties even inside the standards. So, and these slightly different properties sometimes influence the carburizing and the results of carburizing rather strongly. Such an influence has never been found in this case of plasma nitriding or plasma nitrocarburizing. So which is also a very big advantage, because that means for a really very important, very accurate, and very high precision part, the considerations for the steel quality are a little bit less important than for carburizing. So this is, from economical point of view, is very important. So I just try to show which are the differences. So the labor, the additional labor for post-machining and such kind of thing, especially for strengthening, is much smaller for plasma nitriding nitrocarbon than for carburizing. The same for the energy uses. Certainly the energy is lower, and especially as the heating is just for the parts, and we do not heat the furnace, the specific energy needs are much less. Machining costs are less. The material cost is the same. We use the same material. And you see the total cost is with more than 20% less plasma nitrided or plasma nitrocarburized component than for carburized component, which is a big difference. This shaft is one of the most expensive part of a high-speed overlock sewing machine. So to reduce its cost by about 20 to 25% is a very important consideration, and still in the same time you will improve its service behavior. So together, when we go to the conclusions, we can see that plasma nitriding or plasma nitrocarburizing will give us an opportunity to improve both the service behavior of the component and the cost effectiveness, which is extremely important. The compound layer consisting of nitrides and nitrocarbides will prevent seizure and scuffing, so it will give a much better wear behavior than carburizing, even when lubrication will disappear for short times. This is a big problem in most of the textile makeup companies, so confectionery work, that the lubrication could be problematic sometimes, and especially when you start the machines, they practically run in dry conditions. And plasma nitride components will give good results also in this case. And due to the low dimensional changes and low distortion, the overall manufacturing cost will be lower by about 15 to 20%. So that's what was, for us, a very typical case history, a very interesting one, and it more or less is illustrating how we can affect our product design, our economical aspects in the company. Just choosing a good surface engineering method will bring added value, as my friend Professor Bell said. Definitely surface engineering is something which gives added value to the material. So the same material may be used, but with much better results. Thank you very much for your attention.